Alright, so this is our bot that stands up on its own. As you can see here, we have our circuit up top that selectively listens to the accelerometer there, just so that we can keep it cool so it doesn't run too much. And then down here we have our leg systems that can bend right there, or it can bend right there, and together the action moves like that, and then down like that. And then down at the base we have a couple of weights so that it doesn't get too hot, top heavy here. And so we'll show you how that works. Tell us about this.
Alright, so here's the circuit, our schematic for the circuit that we have in our lab project. So we got the lab jack down here, accelerometer right here, we got our 555 timer right there. Now, the accelerometer, we had a little bit of an issue with it. It would overheat if kept running for too long. So, to counteract that, we designed a basic astable circuit here so that we wouldn't have the accelerometer running the whole time. Now, the 555 timer creates a signal that looks like this. Now, what we wanted was something that looked like this. So what we did, we got ourselves a NOT gate running right here. So it inverts the signal from the output, runs through the OR gate doesn't really do anything right now, and goes to the accelerometer. Now this will cause the accelerometer to check whether it's falling in either the X, Y, or Z direction in very short increments. Now, these three, the X, Y, and Z directions, get fed into the analog inputs, and if the LabVIEW code detects that it falls past a certain a given value that we designed, then it will send a high voltage from DAC 0 through the OR gate into the sleep so that the accelerometer is constantly running. Now, we used an OR gate here so that it would, when the high signal comes from DAC 0, it will cause the accelerometer to ignore the basic astable circuit because we don't need that, we don't need the signal from this anymore. So, now we have our accelerometer running constantly, and that will happen until the LabVIEW code decides that it's no longer necessary. And that's pretty much all there is to the circuit.
Alrighty, so this is our circuit here. Now over here we have the 555 timer, which controls the selective listening of the accelerometer, which is going to be over here. And then we have our inverter and our OR gate. You see here that we're only using one input and one output on both of those logic circuits. It's kind of big for it, but that's alright. For our 555 timer, we have it set up in a basic astable circuit diagram here. We have two resistors and one capacitor. These values are fairly low, so we get a very quick timing, something like this. And these all feed into the accelerometer here, which reads out on these pins here, pins X, Y, and Z, and that will give us our acceleration data in the X, Y, and Z direction. We of course have our power rail up here, our 5 volts comes all the way across, and our ground down here, all the way across there. Now our sleep pin is the most important pin. That's the pin that controls whether or not the accelerometer is reading data. It gets its output from this OR gate here, which gets both of its inputs, one from the inverter here and one from the OR here, or rather the lab jack here. Now the lab jack feeds in only when we think we're falling so that we can start listening continuously on this sleep pin here. Now the three, you can't see it here, but the three X, Y, and Z's are these 3 wires here. And they all come out and go into our lab jack right there, as well as the A and 2 there. We are using our lab jack for power for our voltage source here, the 5 volts feeding into this rail, and for the ground feeding into that rail. And that's our circuit. Alrighty, so here's our circuit. As you can see, the little bulb is on there, and here's our LabJack. So, our LabVIEW code here. Now, as you can see, we are periodically testing the accelerometers, and if you look here, you notice the values are changing based on how we orient this. So we use some logic in LabVIEW to make sure that when we get these kind of pulses, we're sending a signal saying, hey, we're falling. Now here's our block diagram. As you can see, it's highly complicated, so I won't explain everything that goes on. But here we have all of our arrays being initialized, and those all feed in to arrays being built based off of the measurements from the X, Y, and Z LabJacks. And then they go into the waveform charts that you saw just a moment ago. So here's our code for the logic to catch the robot. Up here we have our LabJack opening and measuring the voltage on the y-axis. Now the reason we picked the y-axis is because that's the way it was aligned to make sure that we have the maximum voltage when we're falling over. This feeds into this conditional here, which right now is false. If it's false, it just stops the motors. If it's true, however, we take the motor and we kick back our knee and we kick forward our hip, giving ourselves an effective momentum transfer that captures the robot. Now down here as well, we have another conditional. This is for if it's falling forward. And again, the false is just no power to the motors. The true will kick it somewhat forward and back, giving an effective momentum transfer that makes the robot stable. Down here we have our threshold constant. Now we're graphing it in a chart for some debugging here. This was actually one of the biggest parts of the project. We move into this little conditional statement here. Now what this does is tells us when we need to be listening periodically and when we need to be listening continuously. So if this is false, we are only listening periodically. So we set our listen continuously pin to 0, just so that we're not hearing anything. And at that point, what we do is we reset the conditional or the threshold constant. And we do this so that it works, it only happens if we get a true from this wire that goes all the way up and around and actually comes from a shift register. We keep track of this to know when we have moved, because we don't want this constantly resetting the threshold. But if we've moved recently, we do want to reset the threshold. So that's why when this is true, it'll reset the threshold here. And when this is false, it lets the threshold stay constant. Now when this big guy is true here, all it does is it turns on the listen continuously pin and sends our threshold constant straight through. We leave the rest up to these two conditional statements up here.
That's sick. That is sick.
Alright, so what did we learn in this project?
We learned to use circuit-based logic rather than relying solely on the computer.
Well, that's alright. Thanks for watching.